The next section, other convergence tests. This is the last section on tests. All right? So we have seen already basically that everything we've done up to this point, everything we've done has pretty much required, like the comparison tests have required things to be positive, right? But we haven't talked about what would happen if some of those terms were negative. So we're going to have some tests that are going to now work for when we have negatives. So remember what an alternating series is? If we have an alternating series given to us, then it's either going to be like -1 to the n times something, and that creates alternating, starting with negative, or we're going to have -1 to the n minus 1, where we're going to have alternating starting with positive, right? So that's what all alternating series look like. The part right here, the part right there, is basically the part of the formula for the sequence that does not get impacted by the sign, right? This is what controls the sign, and then this is just, you could say that this part is always positive. This is always a positive piece, and then that's just making the signs flip back and forth, all right? So here I say b sub n is the part of the sequence which is always positive. So we have what is called the alternating series test. It only works on alternating series, all right? You cannot use this test if you have a series that doesn't alternate, all right? And the test is really, really easy to use and really nice. Here's the test. So the test says, if you have an alternating series, all right, if you have an alternating series, whether or not it starts negative or positive, doesn't matter which one you have, what you're going to do is you're going to focus all of your attention on that b sub n, all right, the part that's positive, and you're just going to run 2 quick tests on that piece. You're going to look at this and you're going to say, all right, that b sub n, is it decreasing? Is the sequence decreasing? So is this number bigger than the next one? Forget the positive and negative. Just, is that number bigger than that one? Is that one bigger than that one? Is that one bigger than that one? So is it decreasing? That's the first thing. If it is decreasing, and then the second thing is you need that sequence to go to 0. If the sequence goes to 0, then you can conclude that the series converges. So I'll recap. You're given an alternating series. You look at the part of it that's positive. And then you say, is it decreasing, and is the limit of it go to 0? If those 2 conditions are true, then the series converges. Let's do an example. Must go to 0. The limit of the sequence must go to 0. All right, is that an alternating series? Yes. Yes. Let's come up with the formula for this. It starts positive, right? So I'm going to put -1 to the n. What do y'all want? -1 plus 1? Minus 1. Okay, n minus 1. There you go. That's going to create alternating, right? It's going to start with positive. Now, what's the formula that creates 1/2, 1/3, 1/4, 1/5, 1/6, 1/7? 1 over n plus 1. That you have to come up on your own, right? Questions? That's my b sub n. It's the part that's not involved in the alternating part. I want to show 2 things. I want to show, first, that b sub n is decreasing, which really means that b sub n is greater than b sub n plus 1. So the nth one is greater than the one right next to it. The second thing I want to show is that the limit as n goes to infinity of b sub n equals 0. If these 2 things are true, then that original series converges. Which of those 2 seems easier for you to do right now? First one or second one? First one seems easier for you? Yeah? Look at this one. What's the limit as n goes to infinity of that? 0. Right? That's true, isn't it?
Yeah.
This one's true. So that's done, right? One of the two conditions is true. Now, be real careful. Don't confuse this with the end-term test. Remember the pregnancy test, the very first test? We said, hey, what if that thing goes to 0? What does that tell us? Nothing, right? That's in the alternating series test. If the positive part goes to 0, that actually does tell us something. But it's only with an alternating series that this actually matters. So this goes to 0. Let me go through these. So part 1. Let me show it's decreasing. So I need to show this, right? I need to show that that's true. So B sub n is that formula 1 over n plus 1. I need to show that that's bigger than what? B sub n plus 1, which is this formula here with n plus 1 plugged in for n. So what happens if I replace n right here with n plus 1?
1 over n plus 2.
1 over n plus 2, right? 1 over n plus 1 plus 1. So 1 over n plus 2. That's B sub n. That's B sub n plus 1. Is this true? Cross multiply, subtract n on both sides. 2 is bigger than 1. So condition 1 is held. Condition 2, I take the limit as n goes to infinity of the formula 1 over n plus 1, and that equals 0, which is what it needs to equal in order for this to be convergent. So both conditions hold. Therefore, the original series converges by the alternating series test. I like this pace. Let's do another one.
That's how you become that other profession.
Yeah, I'm going to become Dr. Raj. Underneath his thick skin, he was a really good guy. You just had to get through that hard shell he had. All right, good. There's the series. Does it converge or diverge? Right away, I see it's alternating, right? I see it's alternating, that -1 to the n plus 1. So what I'm going to do is I'm going to focus all of my attention on this piece right here, right? That piece is our B sub n. And I'm going to see if these two conditions will hold, the two conditions that are required for alternating series test. So I'm doing the alternating series test right now. And the first condition, let me see, is B sub n greater than B sub n plus 1? This is a question, right? That's what I'm asking. Is this true? I need it to be true. So let me write down B sub n. B sub n is n squared over n cubed plus 1. The question is that bigger than n plus 1 squared over n plus 1 cubed plus 1? So I'm basically saying B sub n is that formula, boom. B sub n plus 1 is what I get when I replace both n's with n plus 1's. And that doesn't look very good, does it? It doesn't look. I could do that. I mean, it's algebra, right? I have another option for you. Another way to show something is decreasing comes from Cal 1. And that's by looking at its derivative and showing that it's always negative, right? I'm going to try that instead. I'm going to treat this like it's a function, okay? I'm going to treat it like it's a function. So I'm going to say, you know, maybe here, I might come back to this. Maybe, don't know yet, okay? Straight-faced, I'm not sure if I want to mess with that or not, right? So instead what I'm going to do is I'm going to take the derivative of this. I'm taking the derivative of a sequence, which is bad notation. It should be a function of x here we're taking derivative of. But when we were doing L'Hopital, we should have been doing a function. So I've been a little bit sketchy with the notation. And the book does the same thing. They do L'Hopital without changing it to a function of x. I mean, we just get to a point where we can't just keep going back. It takes too long. So let's take our derivative. What is it that we want to show that this is what? Negative. We need to show that this is what? Negative, less than 0. Can you prove to me that this derivative will be negative? How do you take derivative of that?
2n.
Quotient rule, right? So 2n times 2n cubed, or n cubed plus 1 minus derivative of the bottom, 3n squared times the top, all over the bottom, what?
3n squared.
Squared. Okay, is that less than 0? So, understand what I've done? Let me clean this up. This is 2n to the 4th plus 2n minus 3n to the 4th all over something. The question is that negative or not? So this is a question I'm asking, right? Is this true? I'm not writing the bottom. Why am I not writing the bottom? It's always positive, right? Because it's something squared, it's always positive. So that will have no impact on the positivity or negativity of this expression, right? Really what matters is what happens in the numerator. And I think we're almost there. Let me keep going. On the top, it turns into 2n minus n to the 4th power over some positive thing. Is that less than 0? I think you could convince yourself right here, couldn't you? Not always, but eventually. Look, when n is 1, this is not negative. But once you get to 2, yeah, this dominates this term. N to the 4th dominates that. So that's a negative. That's always negative. This is always going to be minus some positive number, so that's a negative. Yeah, I think we're good. Yes? First condition's true.
Why isn't it always acting negative?
Because what you're trying to show is that eventually, okay, eventually you have the inequality hold. I think in my notes I say eventually because the book doesn't say eventually, which is confusing. It is eventually. The first few terms aren't going to have an impact on the series. So those first two we can kind of ignore if the inequality is not holding. We just need in the long term for it to hold and continue to hold. All right, second condition, right? What's second condition? Limit n goes to infinity of the, what was it, n squared over n cubed plus 1? We need that to be equal to 0. Is it?
Well, it's infinity or infinity.
L'Hopital, right? So let's do one application of L'Hopital here. We get 2n on top, and on the bottom we get 3n squared. But that's just, we don't do L'Hopital. No, because algebraically you can simplify it first. You never want to use L'Hopital if there's still algebra that can be done. So you go here, and that's fixed over infinity. That goes to 0. Boom. Both conditions hold. This series converges. What do y'all think of that test?
Hate it.
Hate it?
I think it was pretty interesting. I mean, the first part of that test was real weird on this one, but I saw the reason.
You could have done this the other way. If you want to stick with this, is you would actually square this, and then you'd cube that, and then you'd cross multiply, and then terms would start canceling, and eventually you'd get down to something like n is greater than 1 or something like that. And then you'd be like, yeah, that's true. So you could do that. I just wanted to show you that when it comes to decreasing, this was back in 8.1, the very beginning of this chapter, when I was talking about increasing and decreasing sequences. I said one way you can show that a sequence decreases is by taking the derivative of it and showing that it's always negative. So I just want to bring that back up again. All right, the next part of this is something called the alternating series estimation theorem. And due to our time constraints, I'm not going to cover it. I'm going to choose to snip this out. If you'd like, you can watch. I'm sure there's a million, not maybe a million, but there's, I'm sure, several videos online about the alternating series estimation theorem. All it basically does is says, if you have an alternating series, we can actually get a pretty good estimate for the sum of the first so many terms. You know how I said we can only find the sum of certain series, geometric and telescopic? With alternating series, we actually have a way to estimate the sum pretty damn good. And this theorem shows you like how far you would have to go out into the series to get an estimate that's within a certain tolerance. So maybe you're like, I want to get an answer that's like within like 1/1000th of the true answer. This theorem would say, okay, then go out this many terms. And that would be the sum, and you'd be plus or minus 1,000th, and you'd be pretty damn close. It's not really necessary for us to move on, so I'm choosing to say bye-bye. All right, so that skips us down to 8.4.9, absolute convergence. All right, now we move on. No, we're not talking about alternating series anymore. Given any series, we consider a similar series, which is the sum of the absolute value of those terms, right? So what you're doing is you're taking the absolute value of each one. This new series, right, is going to be adding up a bunch of positive numbers, right, for sure. This one up here may not. Let me give you a specific example so you can see this. Let's say we have this series right here. Sine n. So that series, when you look at it, it's sine of 1 plus sine of 2 plus sine of 3 plus forever, right? This is not an alternating series. It doesn't go positive, negative, positive, negative. In fact, it does weird stuff. Like sometimes these are positive and sometimes these are negative. It depends. Do you remember me showing you all the graph of that sequence? And it was like, it looked like the sine curve, but you know, it was just the spots on the sine curve. And that sometimes you would have two that would be positive in a row, and then maybe you would have like, so it's not like plus minus, plus minus, plus minus. It depends on where you are, right? So that's not an alternating series. If I take the absolute value of it, oh, there it is. If I take the absolute value of this right here, absolute value, now I can tell you that every single term is going to be positive, right? Because I'm choosing to take the absolute value, right? So that doesn't always have to give you positive terms, but this one does. Okay, good. That's just, we're just saying, if we start with a series, we can always do this, right? We can always just say, and then look at that series and say, okay, it's a different series. Now we establish a definition. If somebody gives me a series, we will say that that series, you like that? That series is absolutely convergent. We will say that that series is absolutely convergent if this series is convergent. Okay? So this is absolutely convergent if this is convergent. Yes?
So how come on the cheat sheet it uses the word absolutely sometimes? Is there a distinction or is it just emphasis?
Let me continue because we're going to have a theorem, and then the theorem is going to be able to conclude something else, and then maybe the sheet will make more sense then. All right? So if you have a series, we will say it's absolutely convergent if, when you take the absolute value of all the pieces of the series, you get convergence. So I need to show you an example. All right, look at that example there. Is that big enough? Can you all see that? All right. Is this absolutely convergent or not? Is this absolutely convergent? Question mark. So that means what I want you to do is take the absolute value of this and look at that series. So if I take sum n equals 1 to infinity of the absolute value, what effect does that absolute value have?
Just makes it when the top's on a negative.
Yeah, it's like the alternating no longer matters, does it? And the n squared was already always going to be positive, wasn't it? So isn't this just turn it into this series?
Yeah, that's what I was going to ask.
Yeah, it just turns it into that series because the negative one alternating is gone. And that is what type of series? P series. P being 2 greater than 1. This is a convergent series. Right? That converges. So what does that mean? That means we can say that that's absolutely convergent. Right? Careful on what I've said to you, right? You have to be careful because we have not said that that is convergent.
I was just gonna ask that.
We've said that it is absolutely convergent, meaning that when you look at the absolute value, that converges. Now, a big question would be, if this converges, does that force that to converge as well then? You know, like if you have this converge, does that force that to happen as well up there? Like, does that converge as well? And we have a theorem that says that's true, but I haven't given it to you. All right, but that would be a next natural question. Now we have to be extremely careful though. Look at this example here. Let me do an example. Let me do the example first. Where the hell is it?
Theorem?
Yeah, no, yeah. I didn't want to do that yet, define that. Let me just do this. Let's do this one. Sum n equals 1 to infinity of negative 1 to the n over n. We just did that exact problem right here, but I had n squared on the bottom instead of n, didn't I? Okay, is this absolutely convergent? Is this absolutely convergent? No. So you take the absolute value, and then that's just going to turn into harmonic, or P series with P being 1, and that diverges, right? So is it absolutely convergent? No. So this series is not absolutely convergent. But is it convergent? Does this converge? We know that absolutely it doesn't converge, but does that by itself converge? How could you show me whether or not that converges? What test could you run?
Can you do the comparison test?
You could, not, because
Because it alternates? Is that
because you have negatives in here. Comparison only works with positives. But you do have alternating, so you could use the alternating series test, right? Let's do that real quick. Let's see. We know that absolutely it diverges, right? It's not absolutely convergent, but this might still converge. So does it? Let's run the alternating series test on that. So what is the b sub n for us in the problem? If I separate the negative 1 to the n away, what do I have? 1 over n. What are the two things I have to show? Decreasing, right? I need to show that this is decreasing and that the limit equals 0. That's what I have to show, right? Let's do this one. What's the limit of that as n goes to infinity? 0. So I don't need to work. Is that okay? Yeah. That is true, right? All right, does it decrease? So is 1 over n bigger than 1 over n plus 1?
Yes.
Cross multiply, right? That's n plus 1, bigger than n, subtract. This works as well. I'm not going through that in detail, but this means we have convergence. Okay? So look at this. What we're saying is that this series on top, right? This series right here, this series is convergent, right? This series is divergent. Okay? So we have a series that is convergent, but not absolutely convergent, right? We call this conditional convergence. I don't make up the names, all right? Yes?
So then, what would be the difference between like absolutely convergent and then just convergent?
Well, if you're absolutely convergent, then you have to be convergent. That's a theorem I'm going to give you. But you can have, well, wait, say your question again, because I want to be able to answer your question.
So
What-
what's the difference between like absolutely convergent and convergent? Because like the test it converges, but it's not absolutely convergent. Like, so what's the difference?
So absolute convergence is a stronger condition because it means that you converge up there and down here. But I haven't given you the theorem that says that. So if I just say that something is convergent, if I just say, hey, this series is convergent, I cannot just from that tell you whether or not it converges absolutely. But if I tell you it converges absolutely, then I can tell you that the original series converged.
You're looking at it from two different perspectives, right? Like effectively.
So just because it doesn't absolutely converge doesn't mean that it's not convergent at all?
Just because it doesn't absolutely converge. So if it doesn't absolutely converge, so it diverges here, that does not force it to diverge there. Is that your question? That's correct. This is an example.
The first one is looking at negatives, the second one is.
Let me put the theorem up here. This is on your cheat sheets, your table of tests. I think it's the very last one. Can you double check for me? Yeah, it's the very last one. Let me bring it up because so if you're given a series, right? If the absolute value of the terms, so if we have absolute convergence, that forces the original series to converge. So sometimes when we're trying to figure out if a series converges, what we do is we just look at its absolute value. And if the absolute value converges, then that forces the original series to converge.
So if it fails, does it not?
Then it fails, yeah. If this diverges, then you don't know what that does. I think it says, yeah, no, it doesn't say it over there. There's the theorem. If a series is absolutely convergent, then it itself is convergent. Look at this one. All right, so if we were asked to figure out whether or not this one, the question here is, does this converge or diverge? That's the question. Does this converge or does it diverge? I'm not asking about absolute convergence. I'm just saying, does it converge or diverge? So if you start thinking about all your tests, right? Nth term test, right? Very first test we had, right? Nth term, you let n go to infinity, and what you have is on top a bounded function, on the bottom goes to infinity. Anytime you have something that's bounded over infinity, that goes to 0, which tells us nothing. It's not geometric. It's not harmonic. Yes?
Could you squeeze theorem
Okay, so can you squeeze theorem it? Could you? What do you think?
I think so. I think so.
You could probably squeeze theorem this, right?
Yeah.
Let's say, is it an alternating series? Can we do the alternating series test? No, because it's not a perfect like minus, plus, plus, minus. It's not that, right? So what I'm going to do here is I'm going to, I can't do a comparison, right? Can't do a comparison test because some of these terms are negative, right? So what I'm going to do is I'm going to take the absolute value of this. So let's see what happens if I take the absolute value. Right, I'm trying that. And now from this, I'm going to use a squeeze theorem. This is the same as, isn't the numerator, can't you say that if you take the absolute value of the top there, that that has to be less than or equal to 1, but greater than or equal to 0? The top would have to be between those two numbers. And now, to make it look like that, I'm going to divide by n squared everywhere. Oh, I should tell you, I'm using the squeeze theorem. So what I'm doing is I'm trying to see if I can trap this expression between two things that both go to the same number when I take a limit. So I say that this definitely is bigger than or equal to 0, less than or equal to 1. That's just because the sine curve, right? It's between negative 1 and 1. And when you take the absolute value, then you have to be between 0 and 1. And then dividing everything by n squared is just so I can make it look like this. And now let's just take the limit. If you take the limit, I'm just put capital L here. Limit here. We're letting n go to infinity. Where do the two n's go? 0 and 0, which means that this has to go to 0, right?
Yeah.
So what?
It's converging, it's absolutely converging and converging.
Well, what have you shown me? Hold on. What have you shown me?
Well, that,
Absolute value of it converges.
You've shown me that this right here goes to what? 0.
oh, wait, you have to see it's decreasing, yeah?
Well, okay, this is a pivotal moment in this class right now. What have we just shown happens? This sequence goes to 0, which in terms of a series, what happens if you show me that the sequence goes to 0 within a series? What does that tell you?
Oh, wait, nothing.
Nothing.
It's a film, yeah, freaking.
Nothing. You've basically just did the nth term test here, right? I just did the nth term test. So I'm not saying it's wrong. I mean, like, we did it. We got 0, right? Okay, so this thing goes to 0. Well, look. If it would have gone to 1, I would have been happy, right? Or something like that, because then I could say, oh, diverges. But this thing going to 0 tells me nothing about the series. It just tells me that this thing goes to 0. So let me back up, okay? Let me back up. I'm trying to figure out what that does, right? I would like to compare it to something. I think that looks a lot like 1 over n squared.
It does.
It does, right? I'd love to compare it to something. So I'd like to compare this with but I can't. Why can't I compare that to that? Because I got some negatives in here, don't I?
Oh, yeah.
So I can't. So instead of comparing that to that, I'm going to compare the absolute value of this to that. Because the absolute value of that compared to that, then these are positive, aren't they? So instead of this, I'm going to do this. Looking from that series, this one, right? Take the absolute value, and now I'm comparing that series to this, which I'm now free to do because I took the absolute value. What I'm hoping for, what am I hoping for? That this does what? We want this series to do what? Converge, right? Which would force that to converge by the theorem.
Yeah.
So it's like, I can't compare that to anything because I've got negatives in there. But if I look at its absolute value and compare it to something that converges, then that forces that to converge. And the theorem says that if you converge absolutely, then you converge here as well. Does that all make sense?
Yeah.
Right?
With it.
So what would y'all like? Do you want to do this with the inequality, or do you want to do the limit? If you do a limit, yeah, I think the limit might be a little weird because you're going to have to take derivatives and you have absolute values. So I think I'm going to stick with an inequality on this one.